Okay, let's go on with the second part of our cardiac action potential video. And remember, we started out with two different types of cells, autorhythmic cells and our contractile cells. And then we talked about what's actually going on in the autorhythmic cell. We had three steps. We actually had the pacemaker potential, which was this part of the graph, which we started at resting membrane potential of -60. Sodium leaks in through sodium leak channels, causing this pacemaker potential to occur until we reach about our threshold of -40. Once we reach our threshold of -40, then our fast calcium channels open up, calcium rushes in, so we see calcium coming in, we see our graph rising until we actually cross zero. So this portion where the calcium's coming in, our graph is rising, is called depolarization. But when we reach zero, then we reverse membrane potential. And what that does is that is the voltage when we become positive on the inside. That's the voltage that opens up our potassium channels. Potassium then effluxes, leaves the cell, and that's our repolarization. Okay, then we know our sodium potassium pumps kick back in, pump a lot of the sodium back out, a lot of this potassium back in. Calcium pumps start pumping calcium back out. In the meantime, though, what did come in during this depolarization stage especially, these ions start flowing across gap junctions into the adjacent cells. Okay, so what we're going to look at next is how does what has gone on in an autorhythmic cell affect what's going to go on in a contractile cell. Okay, here was our autorhythmic cell, here's our gap junction. Now we're over here in our contractile cell. We can actually see the myosin cross bridges that we talked about last semester. Remember, the cross bridges grab the binding site on the thin filament where we have the tropomyosin and the troponin and the actin molecules. This grabs it and pulls it for the contraction. We can also see calcium inside the sarcoplasmic reticulum because we know calcium has to be released to bind to troponin, shift the tropomyosin threads off. Okay, so notice we have three steps in this action potential, the action potential in the contractile cells, but they're slightly different than the three steps that we had in the autorhythmic cell. So along with three different steps, we also have three different protein channels. The first one is actually a fast calcium channel. This is not a leak channel like we had here. It actually has to be opened by voltage. Then we have a slow calcium channel. Over here we had a fast calcium channel, but then we have the only channel that's basically the same for both, which is the potassium channel. Okay, so we're going to go through three different steps, and the three different steps, though, are not spontaneous. They're not spontaneous, but instead they have to be triggered. Okay, so we actually have to have a stimulus that causes depolarization to happen, because depolarization is going to be caused by this fast sodium channel opening up and sodium rushing in. Now, depolarization over here was calcium rushing in. Depolarization in my contractile cells is sodium rushing in. A little bit more like the depolarization we talked about in the neuron or the skeletal muscle. Okay, now, here in this situation, though, something has to cause that sodium channel to open. And what causes it to open is the influx of ions across the gap junctions. So let's look at that. Notice we have our graph again with our time signature on the bottom, and running upward we have our millivolts. Okay, so our resting membrane potential, instead of being -60 like it was here our resting membrane potential is around -90 a little bit, maybe -93 to -90 millivolts. So we're starting much lower. So at resting membrane potential, that's what we measured the voltage inside, we would get around -90 to 93. And so what has to happen is we need to hit a voltage enough to open up this first channel. So what's going to allow us to hit that voltage, and it's a very quick threshold, a very quick little spike of voltage, which is created by the ions flowing across. So let's look at that.
Positive ions.
Okay, look at our positive ions coming over from what's going on in this cell. Just enough of those to give us a little bit.
Positive ions brings moves the membrane potential to threshold, triggering voltage-gated channels, and initiates depolarization.
So that little bit of movement across caused us to hit that very quick threshold, which is going to open this channel. And our first step here is going to be depolarization, which was triggered by the ions coming across the gap junctions, but causes the opening of the fast sodium channel. So when sodium comes in, it's not going to go gradual like when it was leaking in the autorhythmic cell, but since it's a depolarization, sodium's going to rush in. Therefore, we're going to see our graph rise almost right away. Let's look at that.
Click the sodium channel.
Okay, threshold, open that up. Sodium
Rapid
rushed
influx
in.
of sodium results in depolarization and reversal of the membrane potential from negative inside the cell to positive.
So when sodium rushed in, as soon as we cross 0, now we're positive on the inside, and that was our reversal of membrane potential, and that actually does several things. So again, first we were at resting membrane potential. We had our very quick threshold, opened up our fast sodium channel. Sodium rushed in to the point where we now we reverse our membrane potential. We were negative, now we're positive. That reversal of membrane potential actually causes the sodium channels to start shutting, but causes the the slow calcium channels to actually start opening up. Well, if our sodium channels start closing, then we won't keep rising, but because these calcium channels open up slowly, then we're not going to go negative yet because we still have positive ions. So instead, we're going to have a leveling off that we're going to call a plateau. Let's look at that. So again, now that we've crossed our 0, we reverse membrane potential. It's going to cause the slow calcium channels to open. Calcium will come inside. Now, calcium does two things once it gets inside. It actually triggers the release of more calcium from the sarcoplasmic reticulum, and it starts binding to the troponin, shifting the tropomyosin threads off, making it possible for the cross bridges to grab and to pull for a contraction.
This calcium influx triggers additional calcium release from the sarcoplasmic reticulum. Click the calcium channel to see the slow calcium influx. The slow calcium influx is briefly balanced by a declining potassium efflux, producing a plateau in the action potential tracing.
Okay, so again, once we reverse membrane potential, these shut, this opens. So since we don't have so much rushing in now, we just have a little bit coming in, we flatten out the curve, so to speak. We go into the plateau, and then these are kind of timed. They will start shutting, and our potassium channels were also triggered to start opening up once we reverse membrane potential. So once these start opening up and these shut, then once these are fully opened up, then potassium will leave and we will go back through our repolarization. Let's look at that.
To begin repolarization, the rapid potassium efflux results in repolarization, bringing the membrane potential
back down to the resting membrane potential that we see right there. Now, okay, so now that we have repolarized, we're back at resting membrane potential. Again, we always have to have the sodium-potassium pumps kick in, pump that sodium back out, pump that potassium back in, and then we have to have our calcium pumps pump some of that calcium back out, or we know there's also calcium pumps in that sarcoplasmic reticulum membrane that will pump calcium also back into it. Okay, but remember, it's the calcium that actually, along with ATP, of course, that actually initiates the actual contraction. Now, again, our 3 steps, we had to actually have our quick threshold reach stimulus, and that's not really considered a step, but it does have to happen before the 3 steps can happen. Ions flow across, causes our threshold to be reached. When threshold is reached, our sodium fast sodium channels open up, sodium rushes in. That's our depolarization. Once we cross zero, we reverse membrane potential. And what that does, that causes the sodium channels to shut. It causes the slow calcium channels to open. Calcium comes in, not rushing in, but it comes in. Therefore, we get a plateau. Then our potassium channels start opening up and our calcium channels start closing. Potassium starts effluxing, leaving. We'll go back to our repolarization, back to resting membrane potential. Now, our contraction is occurring during this time, but our contractions are always timed equally. We don't have slow twitch and fast twitch muscle inside of the heart. Because of this plateau, we actually get the same timing on our contraction every time. And then, of course, when we're sending the signal from one cell to another, that keeps the order of the contractions correct. And this is really important because the heart does us no good if we just have individual muscles contracting. We need them all contracting in a specific order so the whole chamber will squeeze at the same time. Okay, so here again we see our autorhythmic cell. Here's going to be our graph for our autorhythmic cell. Here's our contractile cell. Here's going to be the graph for the contractile cell. You would definitely need to know which graph goes with which type of cell and what each part of the graph stands for and what causes each part of the graph. So let's look at that. So again, what's going on? Again, notice when this goes up, we have our depolarization. So again, we have our pacemaker potential, our depolarization, our repolarization. Pacemaker potential was actually what was going on in the autorhythmic cell. It was caused by sodium leaking in. Once we leaked in enough to where we hit threshold, which was -40, then that actually caused our fast calcium channels to open up. Calcium rushed in. There's our depolarization. When we hit zero, we reverse membrane potential, causes our potassium channels to open up, and potassium leaves. Okay, now, then of course we have to have our sodium potassium pumps and our calcium pumps kick back in. But remember, in the meantime, all those ions that came in, they're going to start leaking across our gap junctions to the following cell because they're at a resting membrane potential of -90. But when we get our quick threshold, then our fast sodium channels open up, sodium rushes in, that's our depolarization. Once we cross zero, we reverse membrane potential. That causes our slow calcium channels to open up. Calcium comes in, creates our plateau because our sodium channels have stopped, but calcium's still coming in. Finally, notice how we have a slight decline here. Potassium channels start opening up. Calcium channels start closing. When we just have potassium channels opened up, then we get our repolarization back to our resting membrane potential. And of course, the calcium coming in, the calcium is what initiates the actual contraction. So remember what we said earlier. We said we always have depolarization before contraction and repolarization before relaxation. And of course, that's spreading from cell to cell to cell. Now, obviously, only the contractile cells contract, but this initiates the signal that spreads to those cells.